Quantum time versus quantum space. Dynamic phase meets Berry's phase. In this question from 11.2.1, we are tasked with finding Berry's phase for one cycle of the process in example 11.4, and the hint they say is use equation 11.105 to determine the total phase change and subtract off the dynamical part. You will need to expand theta, or lambda, can't even speak today, equation 11.14 to the first order and omega over omega naught. Okay, so now we're getting to the other parts of adiabatic theorem and its consequences. And the reason why we care is because Berry's phase can produce observable effects. A lot of them are things to deal with in optics. I know that's a main one I've seen before, but there are definitely others. The challenge for you to consider is what is the distinction between the dynamic and geometric phase? If you hang around, we'll find out at the very end. Of course, this is a quasi-long problem, but most of it's in a video. But if you still want the PDF, feel free to comment and I will send you the Patreon link, or you can access it using the link below. Before we jump into today's topic, you should know that my goal is to break down complex physics concepts using exercises from top books. If that sounds like something you'd enjoy, hit the subscribe button and join us in exploring the universe. Now, on to part 1. Alright, so step 1. Let's talk a little bit about what this example 11.4 was before we dive into the numbers and crunching things. So we're tasked with, imagine an electron with charge -e and mass m at rest at the origin in the presence of a magnetic field whose magnitude B0 is constant, but whose direction sweeps out a cone of opening angle alpha, that's what we see here in the diagram, at an angular velocity of omega. Okay, so here we have that happening. So not quite sure how they make this happen, but it's pretty cool. I know they use directed beams, but I haven't seen any papers on it yet. But anyways, what this boils down to is after we solve the time-dependent Schrodinger equation for the spin states and all that other stuff, we see that the adiabatic approximation from the adiabatic theorem means that this omega is much less than omega 1, meaning that the field rotates slowly in comparison with the phase of the unperturbed wave functions. Okay, so that's what we see when we're talking about sudden or sudden expansions, but slow changing in the wave functions. So we're fine, and all this other stuff. Let's dive into this question. So with this main result of the adiabatic regime, where omega is much less than omega 1, the time it takes for the electron to do its thing, as such, we see that lambda, which is just a factor, a phase factor given from the time-dependent Schrodinger equation and its solutions. Um, we see that we need to expand this in terms of omega over omega 1, okay? So if we multiply by 1 and 1 here, just a fancy way of saying, look, we're putting in omega 1 over omega 1 squareds everywhere and omega 1 here. Okay, upon doing so, we see we get a ratio of omega squared to omega 1 squared, and then an extra omega 1, extra omega 1, extra omega 1, all squared squared. So in doing so, we could factor them out from the square root. And that was from 11.14. Okay, so now that we factor out the omega 1 squared from every term, we recondense this into a total square since we had square numerator and denominator. That goes to 1. Now we have a -2 here with the fraction here. Again, that'll come into play very soon. Okay, so because I have a square inside a square root, that's the same as bringing out a factor out front. Okay, now when we apply the regime of the adiabatic approximation, what we observe is that omega is much less than omega 1, so this fraction here goes to 0. And now we have 1 minus 2 times something that's really small. Therefore, we can use the binomial approximation and get rid of the square root in terms of this linearization. Okay, so once we distribute this back in here, we dump this to that term, dump that to that term. We see that that cancels that denominator. And we're left with this lambda factor here of omega 1 minus omega cosine alpha. Again, alpha is the angle that it sweeps at. Okay, So under this regime, equation 11.105, which is the solution from the time-dependent Schrödinger equation, expands as such. Now note that we have a lambda in all these key spots as indicated with the green lambdas, but we note that this numerator looks very suspicious. So let's go ahead and try to clean this up before we proceed forward. So plugging in the lambda down here, but keeping the sine and cosines tidy for now until we can combine them or eliminate them, will save us a lot of board space. So we see that that cancels top and bottom. Beautiful. Because we know that this omega here is supposed to be really small, this really small times that cosine, we're just going to approximate that to 0. Okay. From there then, what we do in the cleanup is we see that we have cosine minus I sine from this part here with the up selection and the down selection over here with the 0. We can combine this into the exponential that's complex. Easy enough. And then here, after the 0, we say that we have omega over omega naught, or omega 1, excuse me. And we know that that's going to end up going to 0. So before we continue, what do you think about this? Drop a comment below with your thoughts. I'd love hearing your interpretations and questions, especially given all the craziness that this chapter has. Okay, so like we talked about previously in the expansion of theta, or theta, lambda, since the regime calls for omega to be much less than omega 1, the ratio here goes to 0, so this whole thing goes to 0 as we see here. Okay, and here we just combine the exponents because now that they're multiplying, we can add the arguments. So now that we have all this set up and we are prompt to plug in lambda here into the exponentials, now that we've condensed everything, the 0 here comes from the fact that the omega over omega 1 went to 0. So anything times 0 is 0, good enough. And then after that, we see that it's just a matter of substituting in and simplifying. Note that it's only chi plus that is left over, so we're in the spin up state, okay? And then notice that we have some common factors here highlighted in purple, so we factor them out, leaving the negative sign on our green lambda, and then we just distribute the negative sign, so we get this up here in the exponential with t over 2. The I can stay out front because we don't care about it in the viewpoint of the phase. And so what this tells us is that in the adiabatic scheme, the electron remains in the state chi plus, or spin up, while acquiring a total phase of everything inside the exponential that's not I. So that would be all of this. Go ahead, put that in good order so we can get rid of the negative signs, because leading with negatives is not always fun. And this tells us the total phase. Okay, now that we have that, we can go straight to stop 2. And upon going to stop 2, what we see is that from equation 11.101, we can calculate the dynamic phase thanks to equation 11.92. So this being the dynamic phase theta, okay, as t, that should give you a hint on our challenge. Knowing that we have energy, but again with an electron and it's orbiting, we know that the energy is going to take that from a h bar omega 1 over 2, okay, ground state harmonic oscillator going on. Okay, so plugging that in, we get minus 1 over h bar here, they cancel. This plus side will go away due to the minus sign here. Omega over 2 can be brought outside because they're constants. And then we're just left with t from our integral. So the dynamic phase summarizes itself as negative omega 1t over 2. Now that we have the total, now that we have dynamic, we can do what the hint suggested, subtract that off and find the geometric. So this leads us straight to stop 3. Again, we have the total and we have the dynamic, so we can find the geometric. And so the geometric phase is, once we substitute in our total, this is our geometric, so we can push that over. Good to go there. This is our geometric phase, and all we do is minus off the dynamic part. We have that, so substitute it in. Negative, negative here creates a positive. And now we see that we have t over 2 in both of them, so factor that out, of course. Once we factor it out, we're left with omega 1 and omega 1 can cancel. Beautiful. And let's simplify this down and see what we got for the berry. So after we simplify that down from canceling, omega omega, factor that out. we get this omega outside, that turns to a 1, no big deal. And so what this tells us is that the time it takes to complete one cycle, capital T, so the period, is equal to 2 pi over omega. And therefore the Berry's phase from 11.95 is equal to the time it takes for a complete cycle minus the initial. Okay, so that's one complete cycle is what we're looking for. Okay. And so if we plug these values for t in, what we see is that the t up here gets a 2 pi omega and a 0. So now we just have to simplify. Omega, omega cancel, beautiful. And then we see here that omega times 0, that's going to be a 0, but anything with the 0 numerator is going to go to 0. Here, this 2 pi simplifies down here to the new numerator. 2 and 2 cancel. Thankfully, we have this bracket times 0, so that goes to 0. This turns to pi, so we just have this bracket times pi. And we see that the Berry's phase here for the spin up state for one complete cycle is equal to pi cosine alpha minus 1. That's a very weird result, but again, has some interesting things happening with later observables. Okay. And so, as Michael Berry puts it, which is a footnote in the book, the dynamic phase answers the question, how long did your trip take? Makes sense for dynamic. And the geometric or Berry's phase is, where have you been? Makes sense for geometric. So, very interesting perspectives here on what we need to consider for total space. Of course, I think phase typically is associated with how long did you take versus Berry's phase, which has a parametric space implementation and implication, especially in the when we're looking at other dynamics of the evolution of the system. It's very important to us, especially if you want to look at a topological point of view. Where have you been means quite a bit. Okay, so this was a fun, albeit rather short video on the topic, so we're definitely going to have more on it later in the further questions, so be prepped for that. But this brings us through all the sections in the book through chapter 11, so the next will just be reinforcements on these topics, which I think we can all use. If this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I just want to take a moment too to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting this channel and joining our community, specifically the Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.